In this course, you'll move from simply using the Cosmos SDK to actively shaping it. We'll unpack the stack, master ABCI++, and design custom modules and consensus-aware logic, so you can ship production-grade, application-specific blockchains with confidence and precision. To work effectively with the Cosmos SDK, you need a clear mental model of 4 pillars: modules, stores, keepers, and messages. Modules are where your business logic lives. Each feature of your chain is a module: staking, bank, governance, or your own custom logic. Stores are the physical data layer, key value stores that hold all committed state across blocks. Keepers are the controlled gateways to that state. They define exactly how modules read and write data, so invariants stay intact. Messages represent user intent. A transaction is just a bundle of messages that, when processed, trigger keepers to update stores according to your module logic. In the Cosmos SDK, you should think in terms of independent building blocks called modules. Each module owns a specific slice of domain logic: bank, staking, governance, or whatever custom business rules you need. Modules don't reach into each other's internals. Instead, they expose clear interfaces, so they can evolve independently and be tested in isolation. All of them plug into a central application wiring layer, which orchestrates how modules interact during each block lifecycle. When you plug a module into a Cosmos SDK app, you actually implement 2 layers. AppModuleBasic is the lightweight, stateless layer. It tells the framework how to encode your types, which interfaces you support, and which CLI commands to expose. No state access yet. AppModule is the full stateful layer. Here you wire in keepers, handle genesis and migrations, and register lifecycle hooks like BeginBlocker and EndBlocker that drive real behavior. So far, we've focused on internal state and modules. Now let's look at how the outside world actually touches your chain. There are 3 main surfaces: CLI, gRPC, and REST. The CLI is for power users and operators. It maps directly to transactions and queries. gRPC provides strongly typed APIs that backend services and SDKs can rely on. REST, usually generated from gRPC, is what frontends and simple scripts tend to use. In a Cosmos SDK app, you should treat state like a bank vault. Nobody gets to touch it directly. Handlers and keepers sit as strict gatekeepers in front of the store. They're the only code allowed to read or mutate state, and they do it through carefully designed methods. That indirection isn't boilerplate. It's how you enforce business invariants, validate assumptions, and keep cross-module interactions safe as your chain evolves. On a Cosmos SDK chain, think of each module's state as living in its own data vault. KKS stores are the primary abstraction. Simple key. Value stores, usually backed by IAVL, giving deterministic, Merkle-proved state. Prefix stores then carve out clean namespaces on top, so different logical areas never collide. Each module owns a dedicated store key, which is how it gets access to its vault and nothing else. When you design store keys, always start from the queries you need to run. Ask, what do I need to iterate over, and how should results be grouped or sorted? Then shape the key so a simple prefix scan gives you exactly that range. Avoid ad hoc string concatenation. Use fixed typed encodings, length prefixed bytes, BEC32 or raw addresses, big endian integers. This keeps ordering and decoding predictable. Also reserve separate prefixes for primary objects, secondary indexes, and module internals. A common pattern is module prefix, then owner address, then an ID. That gives fast lookups per owner and easy pagination. When we talk about the catalyst for state transitions, we're really talking about user intent entering the chain as transactions. Each transaction wraps a concrete request. Transfer tokens, create a position, vote on governance. That intent is explicit and machine checkable. Before the app spends time on full execution, it performs cheap, stateless checks: signatures, basic format, and fees. Only if those pass does the transaction get routed into the heavier stateful logic that can actually change the chain's state. Handlers are the entry point for actually executing a user's intent. Once a transaction has been checked and its message validated, the handler's job is simple: decode that intent and route it into the right keeper methods. Treat handlers as a very thin translation layer, not a place for heavy business logic. In production code, most real work should live in keepers, keeping handlers small, predictable, and easy to reason about. Every transaction also creates an off-chain echo. As handlers and keepers run, they emit structured events, tagged key, value logs that describe what just happened in the state machine. These events don't affect consensus, but they are gold for everything around the chain: indexers, dashboards, wallets, explorers, and monitoring systems. If you design your events well, you get powerful, low latency observability almost for free. You can think of a state change as a request moving through a pipeline. A client submits a transaction. It's just data plus signatures and fees. The anti-handler checks basic validity: signatures, fees, nonces, and account balance. If that passes, routing chooses which module should handle each message. The message server exposes your module's public API. It turns messages into concrete keeper calls. The keeper is where your business rules run and state mutations are prepared. Those mutations are written into the store, updating canonical chain state. Finally, events are emitted so indexers, wallets, and off-chain services can react. As you move toward production, think in terms of small, sharp modules, not a giant blob of business logic. Each module should own a clear piece of state and behavior, with keepers as its only gateway to the store. Other modules should depend on keeper interfaces, not concrete implementations, so you can swap or mock them easily. Keep all validation as close as possible to message handling, and keep pure state transitions dumb and predictable. Avoid God modules that reach into every store. They're impossible to reason about, test, or upgrade safely. Take a breath here. You now have a solid mental model of modules, keepers, stores, and messages. Next, we'll turn that into something you can run, break, and improve. Scaffolding a fresh chain, then wiring up a minimal custom module in Go.